Hello everyone, welcome to another session of Code with a Friend. So today we are going to explore something very common to programmers, which is a data structure called linked list. And my agenda for today is exploring this new library which I have encountered called utilist and see how this library can be used for easily using for linked list in C. But to see how this library actually provides us some benefits, what we should first do is see how we can create some linked lists in the C language itself. So that's, I think, my first part, agenda of the first part of the video. So let's get started. I already have my VS Code opened here, and let me also open the terminal. So I have created a new file, linklist.c. So let me fill it out with some details first, which we will need for any C program. Okay, and we are going to start with a simple structure. And so let me just create this new structure. Usually we called in a linked list. Uh, each you can think of there will be a linked list node, which we call typically a node, and each of the node will have a pointer to the next node. And if it's a double linked list, there will be also a pointer to the previous node. So we'll call this structure list node, which can contain a value for now, and then it will also contain a pointer to the next node. I think we should also, and how do we typically create a node? I am not really familiar, so I'm just going to look it up. So let's look up struct create in C. We'll see create struct in C. Let's look at ncpp reference. So this is a good website which I trust for looking up. And as probably you've seen in previous videos, I'm not really an expert in C. So I am going to do these lookups once in a while. And I'm sure we all do, right? No one of us programs from their head, right? That's not the intention. So if it's like a simple structure, we can probably initialize like this. And if it's a complex structure, probably we want to do a malloc first, and then so malloc would do allocation of that object. So if you are not aware of what a malloc is, uh, it's a function where you have to define the size bytes that you want to allocate for, and then the pointer, for example, in this case, this pointer s1, it would contain the reference for that address, and you can put any value in that memory location. So that's like a very low level construct. So let's try to do in our case. So we have a structure like this. So let's see if we have, and what I'll also try to do is I'll create a type definition so we don't have to add something like this. Something like that. I hope that's a valid syntax. Let me just quickly verify it. Minus O. Let's call it list. Okay. So this is actually a valid syntax. So then let me call it this L node as head, and it should be a pointer. And what we would do is we will try to allocate some memory to this location, and I believe we won't have a definition for malloc here, and that's actually we'll need stdlib for that function because malloc is actually defined in stdlib, and we can choose size of L node here. That should allocate this memory there, and we can call it head next, maybe some value, and head. I think this is not right. Head val should be 10, and head next should be, could be null, or maybe we can have another node called second, and we would also allocate that some memory to the second node. It should also be a pointer. This is actually cleaner, and we assign, let's say second, we assign a val 20, and then we assign this to this, and by default this should be null, but just I think for our sanity we will initialize this to null as well. So what this means is, like, we have a pointer to the head node, we also have a pointer to the second node, but we are not going to use that. So head node has this value 10. It is actually pointing to the second node here. The second node has a value 20, and that is pointing to nothing. So we can actually extract these two things together, and let's just do it like this. And what we will do here, we also want to iterate over the list, so that we can verify that it's actually a linked list or not. So what we would do is, we don't need the second pointer, right? So we can reuse it, so as sort of like a temporary pointer. While second is not null, we will keep on iterating over it and just do a printf. So we'll do print %t, and don't need to mention anything else. We will just do second val, and we will iterate by assigning second next every time. So this basically iterates over the list, and if it's fine, it should probably print that value. So let me try to print that, and now actually it's printing proper. And even in this case, what we can have is, we can allocate another, if you can see, this becomes like a pattern. So we can potentially allocate another pointer, like, let's say, let me call it third pointer, and this third pointer, in the same way, sorry, what's happening? So third, we'll copy third and paste here, and now third contains these values, and second next, instead of being this, what we can call it a little bit different, and then head next will be third. So what essentially we are doing is, like, second is the last element, and this is a third element. So ideally at this point there is only one element, which is like 20, and that's pointing to null here. After we do this, after we do this, at this point we insert third value 30, and that's actually pointing to this. So 30 now actually points to 20, and 20 points to null. After that we insert the head here, and finally head is the first element. So what we have here is 10 pointing to 30 pointing to 20, and then we just use it the same way, the pointer, and dump the output. So let's see if our expectation is actually satisfied or not. So as you can see, the order that we are printing is 10, 30, and 20. So this is one way to add a new element, but ideally what we want to do is We also want to have these functions where we can create a new element and insert a new element at a particular position. So if you see this particular list, at this point, if we want to insert a new element in the list, there are few positions where we can actually insert them. We can insert them at the beginning, we can insert them at the end, and we can insert them arbitrarily in the middle after a specific value. So let's say create actually those functions, and let's see if they run or not. Similarly, this function is actually this operation can be extracted into a function where we simply want to dump the entire value of the list. So that we can do it at multiple steps instead of doing this while loop ourselves every time in our code. So first let's define the function for print list. For print list, what we need to provide is a pointer to head, and we don't want to lose the reference where head is pointing, so we want to keep this value. I would also come what would happen if we don't do that, and then we can also just cut our section here. Right, and let me also print some statement to show that this is the begin, and this should be the end. And if we call this function, let me call the function print list here. Oh yeah, sorry. It should be printf. So yeah, now we can see the list again. And let me just, for the demonstration purpose, I will print it again. And this time, what I would do is I will not use this temp reference. Instead, let me call it reverse. Let me call this as temp, and this as head. And so what this means is basically we are ignoring this pointer, and we have this temp pointer, and we are iterating over that. And we actually are replacing the pointer. So let's see if it actually replaces this or not. So we are actually able to see that, which means it is fine if we don't do that. So probably this happens because we are doing copy by value here. So we are not actually changing the reference. So this is already a variable on stack. Probably that's why we are retaining. So then I guess we are fine. So we'll just change this element to head, or let's keep it temp and just remove it. So this is also new learning for me. I thought it might change it, but it's not changing it. And we can, arbitrarily we can do as many number of times print list here, and it should work fine. Cool. That is awesome. Now I think the next part is we want to insert an element. So let's say at this point we want to insert an element to the beginning of the list. How we would do that? So we would write a function insert begin and our L node head. So at the moment head has some value, so head would point to some value there. So what we can do is we can just do head but we want to create a new pointer there. So let's actually create a new pointer. um, let's do a malloc here and we put the new val, and we also want to say what we want to insert, so we need to be very clear about that. Let's say that's just v, and next we will decide later. So basically, no, actually let's do that now. So new next would be head next now, and our head will now be new. Will this work? Let's see. So if we do this print list head, then we do insert begin head and then some value 40. So our expectation is the list should be something like this. And let's actually just change it like this without doing that. Interesting. So we have this, and we want to also print this list, right? Otherwise we won't know. Interesting. So it did not work. Why it did not work? Because as we had seen before, when we are passing a pointer, it's actually not the real pointer. It's rather a copy of it. If we just do the same operation of print list inside, let's see what happens. So we have now three print lists. First here, then inside, then outside. Okay, so now I think even the first part is happening like 10, 30, 20. Then we see 40, 30, 20, and then we see 10, 30, and 20. So even this insertion is not proper. And let's see why it's not proper. So what we are doing here, we are actually having this new val head is equal to new, and new is actually pointing to that. So we are basically losing the first element essentially. Instead, if we did something like this, let's see what happened. So now you see the first iteration is 10, 30, 20, and we have inserted 40 after the first element, which is also not something we want to do. So essentially, this is also not being right. But the interesting part is here, this is printing fine because we have not actually modified the first element. So since our insert begin is buggy, the next part is showing proper. So let's actually fix first. We want to modify the first element. So how we can do that? So one possible way of doing that is we have this new val which we have assigned. Instead, what we could do is we could possibly change the value of the head itself. That's one possible way. If we do that, and our head val will be v, and head next will be new. What about that? So that actually works, right? Because we just insert this first element and it works in both the cases. But what this actually does, it just modifies the address where head is pointing, but it does not modify the head pointer itself. So this is also a fundamental thing that we want to understand. Um, let's actually also print the addresses. So what we want to do for each of these cases, we also want to print the address where this is located and then the value of it. Let's see if it's at all possible to do that kind of thing, right? So for that, I need to look up how I can print address in C. CP reference address of, but that's I think in C++, right? We are in C. There should be a specifier which I can use for addresses. Let's see, address, pointer address. Can do it with %p perhaps. So %p, then comma. Let's wrap them together into a tuple. And let's see what this prints. Interesting. So here we have some of these values. So now you can see, you can actually see the location where this value is saved. So the first pointer that is pointing to this location where I have this value 10 saved, the second pointer is pointing to this where I have 30 saved, this is this. This is a new location that I'm getting, a new address, and I'm just shifting this value to here. So this address remains the same, but we are printing a different value here. So which means we are not actually modifying, we are actually modifying the address locations. That is actually a not right thing. That's not how a linked list should actually perform. Linked list should not be concerned about, at least the data structure should not be concerned about how the contents of the address locations are and they should behave. Because you can have like a very complex structure. I can possibly have like maybe 5 or 50 different fields, and linked list should not be aware of all of these things. Linked list is just managing the structure of how the data is stored, not internally. So let's change this implementation. How we can change this implementation? So we can change this implementation by, instead of just passing in head itself, we want to modify um, the pointer that head is pointing to. So what we can do is probably we can just pass the address of head. So whenever we pass the address of head, so this becomes a pointer to a pointer. So essentially here, let's remove all of this stuff. We allocate actually new element here like this. This is very clean. So our new next will be null. So this allocates your new structure. And since we want to insert at begin, what we would do is, since we are passing a pointer to a pointer, every time you want to access the fields, you have to dereference it. So the way you dereference it is just, instead of calling head, you would just call star head. And let's see, in this particular case, I want to modify um, head itself. So but before that, I need to set new next as head points to next. So now the new structure that I've created, it's pointing to the first element, or rather, it's pointing to start head. Yeah, it's pointing to start head. And your start head can be new. And in this way, probably we can define this. Let's actually see if this runs. If not, we will debug it again. So what happens here? Now we see this is the address. This is another address. This is another address. This address is now moved here. So essentially our linked list has shifted all of these elements. And the first element is a new address. And that happens whenever we print from here or we print from here. There is no such difference. So let's remove our print statement here. Our insertion is now clear, but it has a bug. Let's say we call this insert begin here. What would happen? Will I be able to call it? We actually are able to call it, but does it do anything? It's actually, where am I inserting 40 here? The first 40 is, it's just being missed, right? So let's say if I'm inserting 50 here, why am I inserting 50? It's not happening. It ideally should insert the first element here. So which means there is a bug when head is null. It's actually not null, right? Because if it was initialized at null, then we can see something different. It's actually not happening here. So I think let's see where are we allocating that. I think we are allocating that somewhere here, but it's not working. Let me actually see that. So let's remove all of these guys and try to do just a print list here. Let's see what happens here. So we got our first element. So this is amazing, right? So even if we have a null value, we allocate a new element and we got it. So which means it's actually fine. I thought we had a bug, but we don't, right? But yeah, I think we should not do a malloc after here to head. So this should be like anytime you do insert begin, it should insert there. And we can now replace all of these elements with corresponding insert begins. Let's say we insert begin and print it for a few more times. 40, 30, 20, 10. And what happens now? So we have 50, then we insert 40, then we insert 30. We're just shifting it to the right and we have a list of 10, 20, 30, 40 like this. So this is pretty neat that we are doing here. That is, I think, one insertion pattern. The other insertion pattern is insert end, where we want to insert at the end of the list. Let's see if we have that. Void insert end. We have a similar way. We'll toss head to it. And how do we change it? So how will insert it? So the new element, let's just do a malloc of that. Size of L node and the new val will be v, new next will be null. And what do we have to do here? We have to iterate through this list. How do we iterate through this list? We should iterate through by just having another temp pointer instead of modifying the actual head pointer, which will reference that, and then while temp points to next is not null. We'll just go to the next element like this, and after that, once we come out of it, we will point like this. So what essentially we are doing is we are iterating over the list, and we are checking if the next should not be null. If the next is null, then we come out and we assign it there, and in that way we expect to insert at end. Let's see if we insert at end here and here. So if we run it, so we have 50, then 40 is inserted first, 30 is inserted first, then the remaining ones are inserted at the end. What actually happens if we insert here? It throws a segmentation fault, right? That's actually interesting. So head is null. And then what we are doing is we are checking if next of a null pointer, is it equal to null or not? So this is a bug. We can possibly call this when it's null, and we can just keep it as a separate case where head is null. We'll just assign head new to head. Should be fine. That actually creates a lot of problem. Why this problem is getting created? So every time we are inserting it, but we should return also from here. I think that's something we missed. Shit. Let's compile it. Let's run it. This time I think it works. We are inserting 50 here. We'll insert at end, insert end. If we change all the insert begins, everything is inserted at end. So we can possibly now remove this pointer printing. We can keep it optional. Something like this. Okay, cool. So now I think it looks much better. Probably let's also keep these as optional. Perhaps the end is fine. Right. Cool. Yeah, this looks much better. So now we have this print list. Now we have insert begin, we have insert end, and we have also tested it. What are the other different things we can possibly have from a linked list? We possibly want to, there are many things we can do. We can insert at index, which means we can say insert an element at nth location. We can insert after value, or we can say find this element within the list and then insert it there. We can also say remove some element. So remove the first element, remove the last element. Those operations are also necessary. We can also mention, I think that's just general search facility. So it'll just be like a linear scan. So let's just implement some of these and see how we go ahead from here. So our main function should now be quite small. We mostly use it for testing. So now let's see what are the other functionality. So a good way to sort of capture it, if for example Java has a good list functionality. So if we see like the Java linked list, what are the things, APIs that they have uh, in Oracle's page, that will give us a good way of seeing what are the APIs that we can define, possibly. So this is like a first API, which is saying Boolean add E adds a specified element to the end of the list. I think this we already have. What we don't have is as a Boolean. What is the return element? So the return element is by collections add true if this collection is changed as a result of the call. So if we are able to insert at the end, I think in here there is no such place where we can't insert, but it still can be compatible. Um, if there's like a failure condition, then possibly we can fail to insert, but we try to keep it quite simple. So that's why we don't say it. Um, let's see what other things we can do. Possibly remove. Yeah, I think remove is a good way, and also saying Boolean. So that says removes the first occurrence of the specified element from the list if it is present, and if the list does not contain the element, it is unchanged. More formally removes the element with lowest index I. Um, let's actually do that. So essentially what this means is like if the list doesn't have that element, it is unchanged. If it has the element, that's the lowest index is removed. So if there is multiple times, we won't bother about it. So to do that, we first need to implement a search function. I think this API also contains a find or a search, something like that. Um, what could be something like get first, index of. I think index of is a good um, indication. Like if it's present, then it will be a valid index, otherwise not. So let's implement index of here. So also let's change insert end to call it at, and insert begin. What do we call it? Insert begin. Should we call it push? Something like this. I don't know, maybe. So let's see index of integer value. Um, Also, a better way could be if we just provide the list node, then we can compare. So let's say we pass some ill node. Let's say just call it fee. So this, and we also need to pass the head. We don't need to modify the head, so just the reference is fine. And what this will do is while head is not null, if head dot value is equals to v dot val, then we also need to return some index. So it will return I there, otherwise we'll keep commenting I. In the end, we will return -1 if we don't find anything. So this is like a reasonable linear search function, right? So which means let's have a list of Another thing, interesting thing which I saw here is add all option, where you can provide like a collection and you can add all of the elements. That's, I think, a good utility to have. So what I'm thinking is probably we can add integer, add all, node head, and then pointer to an array. And we also need to pass how many elements that we are passing for the array. What this will do is we'll start with the size of array. We will call add with head and then array index. So we can pass like an array and then just add all of these elements to the linked list. And if I think of something like this, array, 5-element array, we can initialize them like this. I can call add all address of head and then just the array and then 5. Then I can do a print list of head. Should this compile? So we can insert elements like this, right? So this is like a good utility. And after that, after I do that, I should also be able to find an index of an element. Let's say I want to find the index of 30. Am I able to find it? Oh, I think I can't pass it like this because I'm saying L node. It's not complicated for this purpose. Maybe some generic thing, but so something like this. Then I think it should work. So we I think, okay, yeah, I get it. We also need to traverse the list, right? Otherwise we will just find the same event. Right, so we find it's index 2. That's, I think, what our expected value is. If we pass some element which is not in the list, it will return -1. So I think index is off is also working fine. So we have implemented 2 additional functions, push, add all, index off. What else? So we can possibly implement, I think we wanted to implement remove, right? Add the element to the end of the list. We'll come back to this. Okay, this is actually called add first, show. So we started to actually implement many of these things using utilist, but this is a good divergence that we have encountered. We are trying to see what are the possible APIs that Java linked list exposes, and we are trying to build the same set of APIs in C. It would be a good first exercise, and a follow-up would be replacing all those APIs with utilist. I think many of these overheads that we are maintaining, those can be removed. And these APIs can also be quite generic because now they're very much tied to integer, and if we want to expose the same APIs for maybe float or double, we have to create copies. So I'm hoping Utilist will provide that generic implementation. Then our APIs will be really useful across data types. Okay, so we'll replace that, and now I think we have this add is something at last. What is the difference between add and add last? This method is equivalent. Just, or rather, I mean, it's better not to have any add at all. I mean, it's better to be explicit, right? If we are having one of those two alternatives, just be explicit. Why do we have it? And also, I don't see a point of returning an integer now here. Maybe later on, but I don't see the point. So then these two APIs are very close to each other. We are not also returning anything from here, so this is fine. Clear. Yeah, I think this is actually a good API to implement. But we will go by the order. So let's see, actually go to the descriptions first. So our constructors is not necessarily in our place. Get first returns the first element of the list, but it does not remove, just the returns. So I think that's pretty easy. I don't know why we will need a function for that, but it's something like this. All we need is head. There is one catch though. If head is null, then we have to return something bad. We can possibly return this, or we can be a little bit more creative and we can include limits and say we'll return int min, something like that. Otherwise, we will return the head flag. Pretty easy. Get last returns the last element of the list. That's actually also quite simple option. Get last. We have this L node head. Similarly, if head is null, then we will just return int min, and otherwise we'll keep on traversing while head is not null. Okay. Let's just test these ones out once. Get first, head. Get last. Whoops, first element, last element. Remove first. Okay. It's visible in the screen, right? What I'm implementing side by side. Okay, this video has approximately 10 more minutes. We try to cap it off at 1 hour mark. So after that, we'll break it. But I don't think I'll be able to complete all the APIs by 10 more minutes. But let's see how much we can remove first. So For removal, we have to at least free those locations, right? So that's actually a very important thing. Um, so if we do a malloc, we can also do a free operation. And that's also something I want to try it for removal. Um, we can potentially return any node, even here, right? Um, okay, we'll come back to that later. Let's say integer only. I mean, just for simplicity. Because this is an integer linked list, ideally we can have like a structure linked list, but yeah, anyway, we won't return L node for that purpose. Maybe the structure will be defined internally. That's, I think, the ideal way. Anyway, so we'll do remove first L node. In this particular case, we want to modify the head also. That's why we just need to change head. So the pattern is if we are just reading, then we'll just pass a reference. If we just are, there's a possibility that we might modify, then we have to pass reference to reference and just do that pointer to pointer thing. So remove first, obviously we have to change it. Um, so essentially star head now becomes star head points to next, but what we want to do here is L node temp is star head and we want to free temp. And we also want to keep the value that was there so that we can return this. So the ordering is quite important. Um, let's see if we can remove first here. Remove first address of hand. I think this is screwed up because we are getting get last as something very different. I believe once we print the list, it will be clear. Yeah, it's screwed up. So so essentially we are having this 5 minutes. Let's see if we can complete this. So what we are doing here, we want to modify it, right? So that's what we are doing here. Is this fine if we just let's not do a free thing? The remaining thing is pretty naive. Um, only if we do that free stuff, then we are screwing it up. But ideally we should need to free it up, right? Because should we do, I think so. This is better, right? Yeah, now I think this is better. So let's see the impact of this free. Um, After freeing, if we pass in the value, what would happen? It would just be 0, right? So if I don't do free, then we're returning fine, right? So which is exactly what we want. So the small experiment that I did was, I think the order was quite important of freeing. That's I think essentially what I was saying. We keep a reference temp in head, then we keep also a reference to this value. Actually, we store this value in this integer because we're going to free it soon, and we also change the head pointer to head pointer to next. Otherwise, if we free that, then the entire thing is gone, and we are not able to change anything there. So that's the previous bug that's happening here. But if we change the head pointer and then do a free, then the free is working properly because we cannot get the value back anymore. If we don't free it, we can still get the value back, but ideally we should want to free the memory so that it goes back to the heap. Um, that's I think one good part. So we return the v here, remove first, print list head. Yeah, so I think that's a good content for today's video. Let's catch up in the next session. Bye bye.